Owing to the pandemic, there has been a great void in students' lifestyle with the solitude. But that shouldn't stop us from expanding our wisdom
Owing to the
in any
pandemic,
way
there
possible.
has been a great
Warm
void in
greetings to
students'
everyone
lifestyle
present with us
with
today.
the solitude.
World
But
Space
that
Week
shouldn't
is an
stop
annual international celebration of space science and technology held from 4th to 10th of October. This year, with the theme being Satellites Improve Life, we explore the significant impact of satellites on humanity and what lies in store for the upcoming future. We welcome you all to our last guest lecture of Space Week organized by Pragyan in association with Nakshatra. We would also like to thank Vext India Ventures for being our official media partner.
Today, we have here with us Dr. David Reitze. Thank you for accepting our invitation, sir. It is indeed a privilege to have you here with us today. Dr. David Reitze, currently serving as the Executive Director of LIGO, is an American laser physicist. He is also the Professor of Physics at the University of Florida and served as the scientific spokesman of the LIGO experiment from 2007 to 2011. Despite being an expert in laser spectroscopy, he now specializes in gravitational wave detection. His research primarily focuses on understanding what the gravitational wave has to tell us about the universe. We now have a renowned guest of honor, Dr. David Reitze, to share his insights and thoughts on the topic gravitational wave revolution. Over to you, sir. Thank you.
Thank you very much. I'm honored to be here. First, I hope you can hear me. Yes?
Yes, sir.
Yes, sir. You're audible.
Very good. Okay, thank you. It's a pleasure to be here, and I wish we could all be together in person, but of course we can't. I hope everybody is doing well in this complicated era that we're living in. I'm going to share my screen and give you a brief presentation. It should take about 20 to 25 minutes, and then I hope to get some good questions and be able to have a dialogue with everybody. So let me start sharing my screen. Oops, that's not it. No, that's not what I'm looking for. Bear with me for a moment. There we are. Okay, so hopefully you see that, and you see it in full screen. Yes?
Yes, sir.
Okay, very good. All right, I think we're ready to go. So this is Space Week, and what I want to do is talk to you about very recent results that we've had in gravitational waves. So this is really a revolution in how we observe space and observe the universe. So let me get started right away. And I'm going to start by introducing everybody to something I believe you all know, which is gravity. In particular, when you think about gravity, you think about Newton's laws of gravity, and you think about having two bodies that are close to one another, or maybe not so close to one another. And Newton tells us how those bodies are attracted to one another through the formula that I put here. By the way, there's not much mathematics in this discussion, but a little bit here. So, and what Newton says is that these objects attract each other, and they attract each other basically proportional to their masses and inversely proportional to the distance squared. The problem with Newton's theory, which leads to gravitational waves, is that it doesn't explain how each body knows the other one is there. And for that, it took Einstein. And about 100 years ago, Einstein came up with a much more mathematically complicated theory of gravity, which is encapsulated in this very simple-looking equation, which is actually very, very complex. But what Einstein said is that the bodies actually interact with space itself. So you can think of space as having a geometry. In this case, it's a Cartesian geometry. And when mass is put in that geometry, it changes the geometry. It warps space-time. It bends it. So you can see that when there's no mass, it looks very Cartesian. When there is mass, you can see that all the angles change and they're quite different. And so this is a very, very complicated concept, but a very powerful concept, because it allows you to express the fact that that gravity travels at the speed of light. It also predicts something called gravitational waves. So when objects are orbiting around one another, they're basically, that geometry is fluctuating. It's rippling in space. And as they orbit, they actually radiate gravitational waves, and eventually these two bodies will collide. And this is the heart of gravitational waves. But, and this is the key point, is that gravitational waves have to be measured. How do we measure those gravitational waves? And the answer is we first have to understand what they really are. And this cartoon that I showed you is not really a good explanation of what they are. So let me give you another cartoon, but it's actually more physically meaningful. Gravitational waves are what we would call strains. If any of you are engineers, if any of you have taken physics courses, you know what a strain is. If you apply some force to a body, either stretch it or compress it, it will shrink or grow. That's exactly what happens when objects move in space. Space shrinks and grows. So these two cartoons on the bottom are showing you what happens when a gravitational wave propagates towards you from two objects orbiting around one another. And the key is to look at the form of that equation. So I'm going to do a little example for you. So if I'm very close to the origin of that coordinate system, all right, I don't see much of an effect because L is very small. But if I'm further away, in other words, if I'm measuring over a much longer baseline, I actually see a much bigger effect. And that's actually the key to measuring gravitational waves. So we have bodies orbiting around one another. We want to measure over a large baseline. And by the way, why do I show two different orientations? Because there are two polarizations of gravitational waves, just like there are two polarizations of light. But here's the challenge. Here's the trick. Gravitational waves, even for the most massive objects like black holes orbiting around each other, are very tiny. The delta L over L for two black holes that are much more massive than the sun, say 10 solar masses, about 500 million light years away, so that's quite far away from us, is 10 to the minus 21. So this is a very challenging number to try and get your head around and to try and understand. So how would we possibly measure these? Well, the answer is we use interferometry. But before I get to interferometry, let me tell you why you want to measure gravitational waves. What do they tell us about the universe? I believe in 2019, you had a visit from a colleague of mine, Dr. Fred Robb. He is the head of the LIGO Hanford Observatory. And he told you something called Astronomy 3.0. This is a new generation or a new phase in astronomy. And what I want to tell you is where we're going with that new phase in astronomy. So there are really four fundamental questions that we can ask, and then a bunch of questions underneath those questions. What is the fundamental nature of gravity and matter? That's a really fundamental question. What are black holes? Really, intrinsically, what are they? What can we learn about the highest energy astrophysical events in the universe? What can we learn about the origins of the universe? And I won't go through each of these questions in detail, but as you go through the presentation, you'll see that we're really beginning to have really good answers for these kinds of questions. So now let me tell you how we measure gravitational waves. We use something called an interferometer. And I don't know if you can see my arrow. I hope you can. So we're going to start with a laser. It's a simple cylinder here. The laser is going to emit a laser beam. It's going to get split in two by this object right here. This is a half silvered mirror. We call it a beam splitter. Half of the light will go at 90 degrees this way. Half of the light will continue to go straight this way. And the light will reflect off these end mirrors here and come back. And depending on the length difference, in other words, the difference between this mirror and the beam splitter here and this mirror and the beam splitter here, the light will either constructively interfere in this direction or destructively interfere. In other words, when the light comes back as waves, they either mix in a destructive or constructive way. So now let me do the simulation for you. Right, so as you can see, what's happening is the laser beam is being emitted. The wavelengths, which are the most precise rulers that we have in the universe, laser light is the most precise ruler we have. It goes off and reflects, comes back, and we're color coding the wavelengths just so you can see what's going on here. So right now there's destructive interference. So no light is going over here which records the signal. But as a gravitational wave passes, in other words, as it stretches and compresses space-time, it's actually leading to a signal here. So what you're seeing is that by having a gravitational wave pass over this interferometer, it's changing the length between in orthogonal directions, in perpendicular directions between the two arms, and that is being recorded by this interferometer. So in some sense, we've made a receiver, or like a radio receiver, or a transducer, and we're transducing gravitational waves and turning it into basically a signal that you can look at. So that's the idea. It's actually very complicated to do that, and so let me tell you how we do it in reality. We have two interferometers. The first is the LIGO Livingston interferometer. This one is in Louisiana. This is the picture of the United States. About 3,000 kilometers away, there's a second interferometer in Hanford, Washington, in the northwestern part. And they're identical interferometers in almost every respect. They're just in different parts of the world. And one of the things I want to emphasize is that these interferometers are very large. So this is the building. You can actually see some cars here. They're very tiny on this picture. And the end mirror that you saw is here. The laser is here. The beam splitter is here. There's another mirror off to the left of the figure in the plot here. And the distance that we have to propagate over, where I said h is delta L over L, is 4 kilometers or 4,000 meters. All right, so that's a big distance, but you can then invert this equation, and you can say to yourself, well, I need to measure something that's 10 to the minus 21. Right? That's, again, a very small number. And I need to measure it with a precision of delta L over a distance of 4,000 meters or 4 kilometers. What does that tell me delta L is? It tells you that delta L is about 4 times 10 to the minus 18 meters. So that's a very small number. To put that in perspective, an atom, a hydrogen atom, is about 10 to the minus 10 meters. That's a very microscopic object. The nucleus of a hydrogen atom is a proton. That's 10 to the minus 15 meters. That's an extremely small object. This is 1,000 times smaller than that. So we're measuring displacements with this interferometer to a level of 1/1000th the diameter of the proton. So there's lots of technology in here. I'll say a little bit about it at the end of the talk when I come back to how India will play a role in this. But I'm going to walk through some of the major discoveries that we've made over the past 5 years so you can get a sense of what we're looking at. Right? So the first detection of gravitational waves, we call it GW150914, happened on September 14th, 2015. The data is here. This is a very, very wonderful plot because it shows the data from both Hanford and from Livingston, from both those interferometers I just showed you. The strain is plotted here. So that's the delta L over L, 10 to the minus 21. It's a very brief signal. It only lasts for about 200 milliseconds. But in this data, we were able to invert the data and discover basically what this data was telling us about the nature of the signal. And what it was telling us is that we were detecting 2 black holes colliding and merging together. So you can actually take this data, you can then go back and say, what do Einstein's equations, what does that theory of gravity that Einstein came up with, general relativity, tell us? And it tells us that we saw 2 black holes that were about 1.3 billion light years away. One was about 36 times the mass of the sun, the other one was about 30 times the mass of the sun, orbiting around one another and eventually merging and producing a burst of gravitational waves. So this simple waveform that I'm showing you, this simple squiggles on a graph, actually reveal a tremendous amount about black holes. In fact, this was the first time that we'd ever observed a black hole collision. In fact, it was the first time we ever observed black holes that were more massive than 20 times the mass of the sun. So this was a major discovery. And in fact, it won the Nobel Prize in 2017 for 3 of my colleagues. Let me now come to the second event that was a major event. And I call this event Matter Matters. So this was discovered on August 17th, 2017. This event is in many ways the same, but in fundamental ways really different from the first discovery. And the reason is because this event had matter in it. It had physical atoms. It didn't have atoms. It had neutrons and protons and electrons. So black holes are very simple objects. They're actually just mass and angular momentum, basically the spin of it. But neutron stars are much more complex. They're made of neutrons mostly, and some protons and some other nuclear matter. When they collide, start the movie here, they actually produce not only gravitational waves, which is what that graph is showing you down below, but they produce all kinds of light. They even produce neutrinos. And that collision produced a massive amount of gamma rays, a massive amount of infrared radiation, massive amount of radio waves. So this was really a spectacular collision because it was seen not only in gravitational waves, and I'll again use my arrow to show you, that's the signal. It's a different way of looking at the data, but it is effectively the same kind of data that I showed you with the black holes. But then you also see here the gamma rays. So about 1.5 seconds after these neutron stars collided, they produced a massive amount of gamma rays. Later on, days later, they were producing optical signals, even days later, X-rays. So they produce basically emissions across the entire electromagnetic spectrum. Why is that important? Why do we want to look at objects that have matter in gravitational waves and with telescopes, radio telescopes, gamma ray telescopes? The answer is because it tells us something fundamental about the nature of the universe. One of the questions that physicists ask is, where do elements come from? So we know we ourselves, humans, are made of carbon, we're made of oxygen, we're made of hydrogen. We have other elements like iron and magnesium, things like that in us, calcium for sure. Where do these elements come from? Well, the answer, we know where most of the elements came from, even 50 years ago. Hydrogen and helium came from the Big Bang, the origin of the universe. Most of the lighter elements, like oxygen, fluorine, neon, came from basically stars that exploded, massive stars, supernova. But the elements that are in the red sort of lines there, the elements that are yellow, all right, are primarily produced in these collisions. Because in these collisions, you have the right conditions. You have a lot of nuclear material. It's very dense. Things are happening very fast. It's very energetic. And so to produce elements like gold, like platinum, like silver, you need to have these kinds of conditions. So if you're wearing, I happen to be wearing my gold wedding ring. If you have gold, if you're wearing gold, chances are that was produced in a nuclear reaction that came after a binary neutron star merger. So let's fast forward. More recently, we've discovered some really interesting things that we don't understand. And this is really another thing about gravitational waves, is that we're learning to ask new questions that we don't understand. So this particular merger, I call it the mystery merger. This happened on August 14th, it should be 2019. It was probably a black hole merger, but we don't know that because one of the objects was in a place, had a mass, where it could have either been a neutron star or a black hole. But we don't know. No one knows what this is. So this is forcing us to ask new questions about what kinds of objects exist after cataclysmic explosions that produce black holes and neutron stars that have masses in the range of 2 to 3 solar masses. So this is a puzzle for us. One of the latest results is something we're calling the impossible black hole. All right. This was discovered on May 21st, 2019. We just published this about a month ago. And It's unique for the following reasons. It's the first time we've ever seen truly massive black holes. And I'm going to play a video for you that I think very nicely summarizes how interesting this discovery is.
In May 2019, LIGO discovered the most massive black hole merger ever observed. Two monster black holes collided to form an even more massive object, about 150 times as heavy as the Sun. Not only was this the first time an intermediate mass black hole had ever been directly observed, but one of the monster black holes that created it shouldn't even exist, according to standard theories of how stars die. At the end of their lives, stars of a mass over 10 times larger than our Sun explode in a supernova and leave behind a black hole. But stars with a core mass over 65 times the Sun destroy themselves completely, leaving nothing behind. However, stars with a core mass over 135 solar masses avoid this total destruction, collapsing directly into a black hole. So black holes between 65 and 135 solar masses should not exist. There are two leading ideas how it formed. Maybe it was made of smaller black holes which merged together, building up progressively larger black holes. This could happen in a dense environment like the centre of a galaxy or a globular cluster. Or perhaps a star late in its life collided and merged with another star, making it big enough to form a massive black hole whilst avoiding total destruction. The resulting intermediate mass black hole is the missing link between the two known populations of black holes: stellar mass black holes with masses up to about 60 solar masses, and the supermassive black holes that exist in the centres of all galaxies.
So what this is telling us is that we may have a clue to how supermassive black holes form in the center of most galaxies in the universe. So this was really a remarkable discovery. Now I want to turn to India, and I want to turn to India's role in gravitational wave astronomy. So for the past 7 years, we've been working, we, the LIGO Laboratory, which I lead, has been working closely with several institutes in India to try and bring gravitational wave detection and a LIGO to India. We call it LIGO India. And you can see the concept. This is a concept from the team that's actually designing the facility. And you get the sense that it looks very much the same as the LIGO detectors that we saw in the United States. So this would be a new gravitational wave detector, just as powerful as the detectors that we have in the United States, but it would be in India. So let me tell you a little bit more about it. So the location for this detector is it's actually in Aunda, but it's close to a city called Hingoli, or a district called Hingoli in Maharashtra. The nearest large city is Nanded. You can see it there with the little L shape in the map of India. It's a collaboration between several institutes in India, including the Institute for Plasma Research near Ahmedabad, the Inter-University Center for Astronomy and Astrophysics in Pune, the Rajaramana Center for Advanced Technology, RRCAT in Indore, and the Department of Atomic Energy Directorate of Construction Services and Estate Management in Mumbai, as well as in the US side on the LIGO Laboratory. So those 5 groups or 5 institutions are responsible for the formal project, for building the detector and making it work. But there are a huge number of institutions and universities across India that are actually also involved in this. The target date for observing is 2027, and you can get more information by going to www.ligo-india.in. And I'll say that this is something that is has a very high priority for India, we believe. This was a signing ceremony conducted in Washington, D.C. in early 2016, where the Prime Minister of India was basically present for the signing ceremony. So I'm going to finish up with 2 slides. The first is I've talked a lot about astrophysics. I've talked a lot about gravity and Einstein and black holes and neutron stars. But I want to try and emphasize how important technology is to this. So in order to make LIGO work, in order to make a better gravitational wave interferometer for LIGO India, there are many aspects of research. There are many sort of threads of research that we're looking at. The first is sort of quantum engineered light states. So we're actually taking the ideas of quantum mechanics and using that to craft or manipulate the coherence of light to be able to improve the sensitivity of the interferometer. And these experiments have been going on for a few years, and we're now using them in LIGO, and this will be something in LIGO India. But there's still a lot of research to be done. The next research topic, the next thing that is really important, is basically a material science. So it's a fundamental, how do you design a good material? And the answer has to do with our mirrors. We're looking for materials that when the light reflects off the mirrors, the mirror surfaces don't bounce. Turns out that you might not think that that's important, but it is actually very important. The third thing is deep learning and neural nets. And there are many aspects to this. Of course, you've all heard of artificial intelligence. Well, we're looking at how you use deep learning and multi-layer neural nets to actually be able to take the interferometer signals and better control the interferometer. In other words, better keep the state of the interferometer in a low noise state. And finally, and again, this is a partial list, there's novel laser systems. So we're developing new laser systems at new wavelengths that we believe will be very important for future gravitational wave detectors. And the work that I'm showing here is actually taking place at the RRCAT facility in India. So my last slide is basically to summarize where we are with Astronomy 3.0. And I started by telling you that there are these 4 fundamental questions, and then I broke down a number of sub-questions. We're already starting to have good answers to some of these questions. So we now know that, in part, the heaviest elements of the universe come from binary neutron star mergers. We now know that intermediate mass black holes exist. I didn't tell you this in the presentation, but we now actually know that we can use gravitational waves to measure the expansion of the universe. So these are all very important questions, and within 5 years, since the inception of gravitational wave astronomy, we've been able to answer them. So I'll stop and take questions, but I'll stop with this slide, that gravitational wave astronomy is really a new way to look at a difficult and dark side of the universe, one that we haven't been able to look at before. And I would say that we've entered into a new era in astronomy. And I think most important is that India is poised to play a major role in this new area with the beginning of LIGO India. So I will stop there. Let me see if I can stop. Nope. Did I lose my window?
So you can click on stop sharing in the Teams.
Okay, good. Stop sharing.
Yes, sir.
So, were you able to see my presentation? Is it?
Yes, sir. We were able to see it properly.
Okay.
Thank you, sir. The presentation was extremely insightful. Now we'll proceed with the Q&A session, and I request everyone to put up your questions in the chat box. Sir, we have some questions on our own. So, like, how did you feel when LIGO first detected the presence of gravitational waves, the physical presence of gravitational waves on 14th of September 2015? How did you feel on that day?
It was an interesting set of emotions. First, when I first saw the data, I thought to myself, wow, this is it. We discovered gravitational waves. But I knew that it would take a very long time and a lot of work to be able to convince the world that we detected gravitational waves. So I was sort of simultaneously joyous and worried about all the work that we would have to do to convince the rest of the world that we detected gravitational waves. But it was certainly an amazing moment, I have to say that.
Yeah, it must have indeed been overwhelming.
Okay, so one of the questions that our viewers have asked is, we have a Kagra detector in Japan also. So why do we need so many detectors?
Very good question. And I didn't touch too much on that. The one thing that a gravitational wave detector cannot do on its own is tell you where the signal came from. So the analogy I would use is a microphone. An interferometer is really like a microphone. It picks up sound signals from all different directions, but it doesn't really tell you where, in which direction it came from. So in order to have directionality, in order to be able to say the gravitational wave came from over there and have optical telescopes point over there, you have to have multiple interferometers. It turns out that 3 is about the minimum that you need. It's basically triangulation. 4 is better. Right? So we have the LIGO detectors, we have the Virgo detector in Italy, and we have now Kagra just coming out, and then we'll have LIGO India. 5 turns out to be even better. And the reason for that is that the more detectors you have, and the more they're actually distributed in far places on the Earth. First of all, these detectors don't always operate. They're not reliable. They operate about 70%, 80% of the time. So at any given time, 1 or 2 of them are not going to be working. And second, by the fact that they're far away, you actually get basically better timing information for that. So there's a real compelling reason to have multiple detectors.
Oh, that makes sense, sir.
Sir, these detectors must be extremely sensitive to the environmental vibration, like the quantum fluctuation and everything. So how does LIGO overcome this challenge of eliminating the noise?
There are hundreds of noise sources that we have to overcome. Some of them are very fundamental. The fundamental ones are the quantum nature of light, the fact that photons have random arrival times. Some of them are, in the last slide I showed you, one of the last slides I showed you, the fact that the mirrors actually vibrate. That's called Brownian noise. So those are the biggest one, actually, the one that's probably the most problematic for us is the ground itself. These interferometers are put on the ground. The ground is vibrating, and so we have to go to great lengths to isolate the mirrors and the interferometer from the vibration. So we have very sophisticated seismic isolation systems that actually attenuate the noise, the ground noise, by a factor of 1 trillion, 10 to the 12. So those are 3. But then we have noises due to the fact that the laser is not perfect. We have noises due to the fact that the control systems have electronics. The electronics have noise. The vacuum. I didn't tell you about the vacuum system. The vacuum system is itself a very complicated thing. Even though it's a great vacuum, it's not a perfect vacuum. So the light can come and hit a molecule, and that leads to noise. So there are hundreds of noise sources. So the way we deal with this is we try to calculate all of them. We try and say, what are those noise sources? And then we design our system to basically beat those noise sources as we understand them. And the reason this took, LIGO got started in the 1970s, or at least the precursor. The reason this took 40 years is because it took that long to beat down all those noise sources and actually make a detector that was sensitive enough to detect a gravitational wave.
That's really interesting, sir.
So following up on that, how does SNR ratio differ for like advanced LIGO, and Virgo? Like we are basically using the same equipment, right? So how does it change from LIGO to advanced LIGO to Virgo?
Yeah, so the observatories are the same, the facilities, the vacuum systems, but the detectors themselves are quite different. So the initial LIGO detector, trying to give you a good analogy, the initial LIGO detector was like a tuk-tuk, okay? All right, it worked, but it wasn't very sensitive. The advanced LIGO detector is like a Ferrari, all right? Or a Mercedes-Benz. It's just a much better detector. All right, we completely rebuilt the detector from initial LIGO to advanced LIGO. Virgo, the concepts behind these detectors are all the same, but the people that build them and the designs that go into them were different. So Virgo is a little bit different than LIGO. You talked about Cagra. Cagra is actually quite different from both. Cagra uses cryogenics. The mirrors in Virgo are actually held at 10 degrees Kelvin, so they're just a little bit above absolute zero. And the reason for that is that that makes the motions of the mirrors that much less. So even though they sort of all at the top level look the same, they're actually quite different. The two advanced LIGO detectors are actually almost identical. They're not perfectly identical, but they're almost identical.
And following up on that, like we have seen that there are a lot of noises on the Earth. So why don't we take a project that can go up to space? Like LISA was supposed to go up in 2022, I guess, but it has been postponing for years now. So is it still on or?
Yes, it is. So LISA is Laser Interferometer Space Antenna. LISA is very important. It actually looks at a different class of gravitational wave emissions. So if you think about electromagnetic spectrum, right? You know, on the one hand we have gamma rays, very high frequency. On the other hand, we have radio waves, very low frequency. And we have infrared. We have optical, UV, X-ray, all the way up. Gravitational waves are the same. There's a spectrum. LIGO and Virgo and LIGO India detect very much the high frequency end of gravitational waves. LISA goes a little bit further down, and it actually sees a different class of sources, more massive black holes. So LISA will see all kinds of intermediate mass black holes, and they see supermassive black holes. It will probe phase transitions in the early universe. It will actually see white dwarfs merging. So LISA is still going to go forward. In fact, I believe the current launch date is 2034, so it's still many years away. But LISA will become, I would say, a very important part of gravitational wave astronomy, just like gamma ray telescopes and X-ray telescopes and optical telescopes are very important parts of electromagnetic astronomy.
Okay, sir.
Sir, how is LIGO's project benefiting other areas of research?
That's a great question. There are three things I want to say in answer to that question. The first is that, first of all, LIGO is asking fundamental questions. Gravitational wave astronomy asks fundamental questions. And the way we learn about the universe, because we're curious human beings, is to build new instruments. When somebody built the Leo built the microscope, he looked and saw little, bacteria roaming around. We learned something new. When the laser was built, and we shined it on something, we learned something new. When the first telescope was Galileo, we learned something new. So we're learning something fundamental. Okay, so I think that in itself is very important. But I think the question sort of says, how does the technology impact our daily lives? Right? And the answer is in a couple of ways. So first of all, we work very closely with industry. So our lasers are the best lasers that have ever been made. The mirrors that we use are the best mirrors that have ever been polished and ever been coated. And by sort of pushing the state of the art, now mirror coaters can make mirrors that are great for other things. Let me give you one example. We talked about seismic isolation. The semiconductor industry is trying to push towards ever more narrow and narrow line features. I think the current state of the art is so if you have an iPhone or a Google phone, whatever kind of phone you have, all right. If you look at the chip in there, the features are very small, but they want to make them smaller because they can obviously put more transistors and make more powerful CPUs and phones. They're limited by their ability to do lithography because they're limited by vibrations. So the vibration technology, the vibration isolation technology that we use is actually being looked at. It's not being adopted yet, but it's being looked at by semiconductor industries because we think it can actually help them make more uniform. So there are two examples. But the third example, I think, may be the most important one. And that's that the people that work on LIGO We have graduate students, we have undergraduates like NIT Trichy, who come, who work. Maybe they get PhDs, maybe they get postdocs. They learn something, but then they take that knowledge and go off and do something else. So some of our graduates are now working for Google. Some of them are now working for Facebook. Some of them are now working for Infosys. These are all people that have been trained in a very narrow scientific discipline that are taking that knowledge and applying it elsewhere. I haven't talked at all about computer algorithm development, but in order to search the data, we have to develop very sophisticated computer algorithms, and they have to work very rapidly and very reliably. And so those kinds of things, they migrate into other things. So, and it goes the other way. We actually, as I said, artificial intelligence and deep learning is a big thing. So we're starting to bring that into what we're doing too. So it goes both ways.
So also following up on that, is there any chance that we will be able to detect early signatures of G waves from the early universe, from the detectors on the ground level?
Yeah, that's a great question. The answer is not likely. And it comes back to the frequency. So if you look at the emissions from the early universe, from the Big Bang, they're very long wavelengths. So the wavelengths from the Big Bang are on the size scale of the universe. Our detectors are sensitive to wavelengths that are hundreds of kilometers long. Right? So our detectors just aren't tuned for that detection. Now, if we do detect we call it a stochastic background. If we were to detect something that we could not attribute to anything but the early universe, that would be revolutionary in itself, because it changes the way we think about cosmology. More likely, there are projects, there's another kind of gravitational wave detector that actually looks at something called the cosmic microwave background. In particular, it looks at the polarizations of the cosmic microwave background. And by measuring the different polarizations as a function of position on the sky, you can actually infer how gravitational waves imprinted on the cosmic microwave background. So these experiments are ongoing, and it's very possible that within the next few years, 5, 10, we don't know, that we'll actually be able to see gravitational waves from the residue of the Big Bang. And that would, again, be a very revolutionary thing.
Sir, since G waves currently concern black hole merger, what are your opinions on the recently given Nobel Prize to Sir Roger Penrose for his work on black hole?
Congratulations, Roger. That's the first thing I'll say. I'll say a couple of things. Obviously, the work was very important work. Roger did some very important work in the early days to try and understand sort of the fundamentals of black holes. And Reinhard Genzel and Andrea Ghez, who's very close to where I am, did some really seminal observations to prove effectively that supermassive black holes exist in the universe. So I think it's great. That's that they won. They certainly are very deserving. I congratulate them. But I think it actually shows you how important looking at the universe is. The Nobel Prize is recognizing this is the third or fourth Nobel Prize in the past 5 years that is really directed towards space and directed towards understanding the universe. So I think that's important. The other thing I will say that I think is great is that this is only the fourth time a woman has won the Nobel Prize in physics. But guess what? 2 years ago, another woman won the Nobel Prize in physics. So the first Nobel Prize in physics for a woman came in 1903. The second came in 1963. The third came in 2018. The fourth came in 2020. So I'm hoping we'll see a lot more Nobel Prizes for women.
This definitely looks inspiring for women around India and world to continue and pursue sciences. Similarly, when we saw that in 1960s, they started building up, they started working on the G-wave detectors. That was the time. It took us like around 50, 60 years to get our first detection. So do you think it will take this much time to come up with a new major breakthrough in this science or any other science in dark matter or all?
No, I think actually it goes the other way. Whenever you have a new kind of instrument, you start to discover things that you didn't even anticipate. Right? So I mean, I would argue, we're talking about Nobel Prizes. I think some of the discoveries that I talked about, we talked about the first Nobel Prize. I think there are other Nobel Prizes in the discoveries that LIGO has already made for people. So I would argue that there was already big things happening there. You talk about dark matter, dark energy. I mean, dark energy has also won a Nobel Prize. Dark matter has not yet been detected. I think that once it is detected, and it very well actually could be, there could be some connections to gravitational waves, but they're very tenuous at this point. I think it'll lead to more rapid and revolutionary discoveries. But the way things get learned, the way knowledge comes into our brains is twofold. One is that we have very smart people who develop theories and who think like Einstein for how do I think about new ways of thinking about gravity. Others are building instruments, and I think both of them are very, very important. So when new instruments get built, we discover new things. So I think the pace of knowledge and revolution will actually accelerate as we go forward.
Sir, how will G-waves help us in measuring the expansion constant of the universe?
Right, so I didn't really talk about that. So the way we now measure the expansion of the universe, there are two different ways to measure them. One is using basically something called a type 1a supernova. Basically, it's a very standard emitter, and by measuring its redshift, you can actually then calculate how far away it is and how fast it's moving away from us. The other way is to look at the early universe Planck data, and you can infer the expansion from that. Those are two different ways to look at it. They actually don't agree. So one of the big puzzles in cosmology is why there's a tension between what electromagnetic type 1a supernovas tell us the expansion rate is, and what Planck, the early universe observations tell us. So gravitational waves do it a little bit differently. And the way we do it, and again, I didn't talk much about this, is the fact that gravitational waves are they're perfect emitters. What do I mean by that? I mean that if you detect a gravitational wave signal and you know where it came from and you know how far it came from, all right, and you know the source, you know that it was two black holes, all right, immediately, because gravitational waves propagate, and their amplitude decays is 1 over r, all right, you have a perfect measure of the distance and what's known as the luminosity distance between those waves. So by knowing where it came from and associating it with, usually it would be associated with another galaxy, all right, it doesn't matter how far close to us it was or how far away it is. It gives us a Hubble constant for that. And actually, the more we measure, the better we can measure this expansion rate through the measurement of the Hubble constant. And right now, we're not competitive with the supernova folks in the early universe people, but we will be. I would say in the next 5 years, we'll actually start to have gravitational wave Hubble constant measurements that are actually quite competitive. And what's, I think, really important about gravitational waves is they don't care about where you are. In other words, they're good in the electromagnetic type 1a supernova regime, and they're also good in the early universe regime. It just depends on how far away you can measure them. So in order to really do this well, we need to build new detectors, which we're thinking about doing, actually. But we should be able to span the entire range of what we call redshifts, or Z's, to be able to do this. So gravitational wave cosmology will be something that's really important, I think, in the next 10 years.
Oh, that is inspiring. So let's say if we have to explain to a normal person that how do we estimate parameters from a signal or using Fisher matrix, which sounds very mathematical, but how would we explain it to a general audience? Like how do we estimate the parameters from a signal?
Yeah, I'm going to try and share my screen. Okay, so hopefully you can see my screen.
Yes, sir.
So let me look. I'm not gonna go into full screen mode. I'm just gonna ask you to look at this data right here. All right, and you can concentrate either on the orange curve or the blue curve. There are several features of this data that stand out qualitatively. All right, there's noise on the data, but the first thing you can see is that the amplitude of the wave is increasing. So as you go forward in time, later in time, right, the amplitude of the wave is increasing. That's number one. Second thing you notice is that the frequency of the wave is also increasing. In other words, over here the wavelengths are quite long, but as you get closer and closer, the wavelengths get shorter and shorter. So, and then the other thing you note is that at some point, at some frequency, even though we're not doing a frequency plot here, the wavelength, the wave goes away, and that's the point at which the merger happens. So, sort of very qualitatively, those three features tell you most of what you need to know in a probabilistic parameter estimation, Bayesian Fisher matrix sense. So the end frequency, where the gravitational wave disappears, tells you something about the final mass. The way the frequency changes with time, the fact that the frequency is getting shorter, we call that a chirp. All right, the frequency is getting higher, the wavelengths are getting shorter as we go. That's called a chirp. That tells you something about the two initial masses. It doesn't distinguish them. It doesn't identify one mass versus the other mass, but it gives you sort of an algebraic formula that tells you if one mass is this, the other mass is that. All right, and then based on the fact that you have a final mass, that allows you to run inference models to do that. And then the third thing that's important is, again, the amplitude of the wave. And once you know the masses of the object, all right, that immediately tells you what they're radiating, and just looking at the amplitude tells you how far away they are. And then the other thing that comes into this, and we talked about it earlier, is the fact that if you have multiple signals, notice this is very important. Notice it says LIGO data shifted. It had to be shifted by 7 milliseconds because of the difference in arrival times, because one detector was further away from the event than the other detector. So if you have multiple detectors, by taking those time shifts into account, you actually get the position. So yeah, you can run complicated, and the way we do this actually is we use basically Bayesian inference. We take the waveforms that we see, we model them against model waveforms, and from that we infer the parameters.
Okay, that sounds good. So sir, there's a question in the chat box that we have observed binary systems. Have we ever observed a system where 3 stars or 3 black holes are rotating around each other?
No, not yet. Although there's some speculation that the latest observation, GW 1905-21, might have been in an area known as in the center of a galaxy, something known as an AGN or active galactic nuclei, because there's some hint that there was actually some electromagnetic radiation. So in this case, it might have been that you might have had a supermassive black hole that was in proximity to the two massive black holes that I showed you earlier. But no, we don't have any solid evidence that we have seen a triple, an event that had 3 black holes in it.
Is there a possibility in the future that our understanding of gravity is completely destroyed by a new detection? Like maybe there's a detection like recently we found an impossible black hole kind of thing. And is there a possibility our understanding of gravity is very, very fragile at a point? It becomes a fragile after that point.
Yeah, when you asked the question, my initial response was, "Boy, I hope so." The way we learn about the universe is by breaking the current theories, or basically discovering things that basically point to how the theories are flawed. So the reason Newtonian gravity, all right, was overcome by Einstein and general relativity was that there were fundamental problems, actually with electromagnetism, not just gravity, with electromagnetism, that led Einstein first to think about special theory of relativity and the general theory of relativity. So what we're doing is we're probing with gravitational waves, we're probing space-time in some sense in the most extreme conditions. All right, these, when these objects are orbiting around one another, these two black holes, they're orbiting at significant fractions of the speed of light, and they're very massive. So the space-time is really warping. Kip Thorne, I'll quote Kip Thorne, who says that you're looking at a storm in space-time. What that really means is that these are places where we haven't yet looked at and where things are changing very dynamically. So it's very possible that we could, for example, start to see deviations from general relativity. Where would those deviations come from? Well, there are a number of places we're looking. The first place is the waveforms that I showed you, those squiggles that I showed you earlier, right? If the frequency changes in a way that's not predicted by general relativity, right, that indicates that gravitational waves might be absorbed. That would be fundamentally different from what Einstein says. Einstein says gravitational waves don't interact with matter. So that would be the first clue. Second clue would be, for example, is there some quantum property of the black hole? Black holes are very simple and very complicated at the same time. Is there some quantum property of the black hole that you can see by looking at the gravitational wave signal? People have proposed things called firewalls. This gets into a lot of complicated physics having to do with information theory. But it might be possible that the gravitational waves contain some evidence for that. So if we were to see evidence for that, I think that would be the thing that would really sort of start people thinking, what's the next big thing? We know that one of the big, I would say, outstanding problems in physics is that you have quantum mechanics, which talks about atoms and subatomic particles, and you have general relativity, which talks about the large-scale structure of the universe and gravity. And no one's been able to make those theories come together. The way people are trying to do it now, and they've been trying for 40 years, 50 years, is string theory. But it hasn't worked. I mean, string theory is very complicated. It hasn't led to many predictable, in fact, if any, real things. So you really need experimental guidance here. Now, having said all this, if you ask me, am I willing to bet? Am I willing to basically take $1 out and say that we will discover that general relativity is wrong? I would not make that bet. I'm not ready to make that bet.
Okay, sir. So since nowadays we see like there are a lot of citizen astronomers that make a lot of discoveries. So what do you think is the impact of platforms like Berkeley Open Software and then Zoo Inverse, where people can give their inputs? So what do you think this kind of impact has for the future scientists and future students who want to work in the field?
Well, I think it's great. So you talked about the BOINC, Berkeley Open Network. We actually, LIGO actually uses BOINC to search for neutron star gravitational waves. So go to Einstein at home. The second thing is you talked about Zooniverse. We actually, one of the problems what we have with our detectors is that there's a lot of noise, as we talked about earlier. So we use actually machine learning and classification that are trained by humans through something called Gravity Spy. Right? And so this is citizen science that we use. There have been a number of, if I look at astronomy, there's a number of examples of amateur astronomers that have discovered comets and things like that. So I'm a big fan of citizen science, and I'll even go further and say that I didn't talk about it in the presentation, but anybody in the world can look at LIGO data. So you can download LIGO data. Just go to the Gravitational Wave Open Science Center, GWOSC, GWOSC. You can download LIGO data and look for gravitational wave signals yourself. Maybe you'll find something we didn't. That would be great.
Going on this trend only, recently we have seen a huge strides in quantum computing, Google making their own quantum computers and all. Do you think it is really helpful for LIGO as such?
Yeah, so I think have a colleague named John Preskill who's big in quantum computing. Um, he basically says that we're sort of in the transistor era of quantum computing, where we're just learning how to manipulate qubits. We're learning how to isolate them from the environments. We're not yet at a place where you can contemplate large-scale quantum computing. So I think from the standpoint of quantum computing technology, it's going to be a while before it has an impact in certainly what we do. I mean, what people are looking at for quantum computing is more quantum simulators. Basically, can you simulate quantum systems more effectively in a quantum computer than you can with a classical computer? And I think that's where a lot of effort is going right now. But I think as far as LIGO goes, no one that I talked to was thinking about quantum computing for LIGO yet. But that could change. I mean, if there's a big breakthrough in the next few years, who knows?
I guess we are done with our questions. I'll let Mridula ask one last question.
Sir, one last question before we wrap up the session. So, what advice would you give to a student currently pursuing engineering who's interested into entering into the field of gravitational wave astronomy?
I would say it's a great field to get into, and a lot of the development of the detectors that we've done comes about from engineers. Some of the how do I say this? Some of the most important people in LIGO are engineers. All right, we could not have made this work without engineers. We have great mechanical engineers, we have great optical engineers, we have great laser engineers, we have great engineers that work on computer algorithm developments. I think it's a great wide open field. I think, again, India is going to become much more important in this field in the next, hopefully, 5 to 10 years. I would say that there's a lot you can learn, and there's a lot you can contribute. So I would hope that it's intellectually exciting. You work with a lot of people. You're discovering new things about the universe. What could be more fun than that? That's just great. So.
Definitely.
That was really insightful, sir. Thank you so much, sir, for taking time out of your busy schedule to enrich us with the exuberance of your immense knowledge. It was indeed a pleasure to have you here with us today. And I really hope we had this conversation in offline platform.
I'm glad too. Thank you very much. I do get, in the current COVID-19 era, I don't travel, but once I do travel, I will come to India. So I hope to meet with you personally someday. Okay?
Sure.
Yes, sir. Thank you, sir.
All right. Thank you very much.
Thank you. Thank you.
Internationally, World Space Week had more than 3,500 events, and we are glad to be a part of it. And we look forward to bring you an array of events and guest lectures for the Space Week next year. We thank everyone for joining with us today, and we also thank Vext India Ventures for being our official media partners. Until then, keep looking beyond the stars. Thank you. Have a nice day.
Thank you, and have a nice day.
Okay?
Yes, sir. We can leave, sir.
We're out?
Thank you, sir.
Good.
Yes, sir.
So I hope that went well. I wasn't sure. I saw a little message saying that my screen wasn't sharing, but I hope my screen was actually working the whole time.
Oh, yes, sir. Definitely.
Yes, sir, it was.
Yes, sir.
Okay, good. So anyway, thanks so much. Enjoy your Sunday. This is Sunday for you, so enjoy your Sunday. All right?
Thank you.
Yes, sir.
Thanks for being all smooth, and I'll hopefully see you sometime.
Bye, sir.
Bye.
Bye, sir.
Bye.